Today, we are taking a deep breath and plunging into a very specialized world.
Very specialized.
The cutting-edge innovations in industrial cutting tools. We've sourced this directly from ISCAR's 2025 product review materials.
Right.
Now, when we say industrial cutting tools, I know your mind might go to boring spreadsheets, maybe blocks of steel.
That's right.
But this industry is where the physical reality of all modern manufacturing gets defined.
I mean, from rockets to medical.
Point of creation, really.
Exactly. And the material we have is, well, it's intensely technical. It's full of jargon about geometries and coatings.
Oh, absolutely.
So our mission is to filter all that. We want to give you the fast track to understanding the core trends, the surprising efficiencies, and really the pure genius driving this stuff. We're decoding what happens at that microscopic point of contact. And this review is a big moment for ISCAR. They have this lovely framing for it. They call it gathering stones.
Gathering stones, I like that.
Yeah, it's a process where they step back, they evaluate their achievements, and then look forward at where the industry is really heading. A breakthrough in this field isn't always some, massive new invention.
Mm-hmm.
It's often a highly engineered refinement, a tiny shift in geometry or chemistry that just delivers a game-changing gain in efficiency.
We're hunting for that multiplier effect. Okay, I think let's unpack this.
Let's do it.
Let's start where the magic really begins. Material science. We're talking about the development of the actual grades.
The tungsten carbides, ceramics, cubic boron nitride, or CBN.
Yes, this is the absolute foundation, and it requires this lockstep collaboration between engineers, metallurgists, and technologists.
It's a constant arms race. I mean, every year manufacturers are introducing stronger, lighter, more heat-resistant alloys.
Especially in aerospace.
Especially in aerospace and energy. So if your cutting edge can't handle the immense heat and pressure of modern machining, the rest of the tool it's obsolete. No matter how clever the design is, you're always trying to expand that performance envelope.
But without breaking the bank.
Exactly, without breaking the bank.
And ISCAR gave us 3 specific new material grades for 2025 that really show this strategy. So first up, let's look at IC1024.
Okay.
The practical application here is turning hard steel. Specifically, up to HRC 62. Now, for anyone not familiar, HRC 62 is extremely hard.
Yeah, we're talking specialized bearings, hardened molds. It's serious stuff.
Not something you cut casually.
Not at all. And the real breakthrough with IC1024 isn't just that it can cut it, it's the economics of how it cuts it.
Ah, okay.
Traditionally, to machine steel that hard, you're immediately forced into using things like ceramics or CBN, which are often just prohibitively expensive.
Right, for any kind of high volume work.
Right. Exactly. So by developing a carbide grade that can handle that hardness reliably, IC224 becomes this critical, cost-effective alternative. It means manufacturers can finally process these super hard components without that steep tooling cost.
So they're solving a major cost bottleneck. That makes total sense.
It's balancing performance with value.
Okay, next up they gave us IC706, and this one has a very specific upgrade, a titanium diboride coating.
And that coating, that tells you exactly what it's for.
Titanium alloys.
Titanium alloys. Titanium is just notorious for being sticky.
Sticky.
And when you machine it, the material tends to chemically react with the tool and literally weld itself to the cutting edge.
Wow.
Yeah, it leads to built-up edge, rapid wear, catastrophic failure. So a specialized coating like this, it acts as a barrier, it enhances performance, increases tool life, and lets you push the speed limits.
So it's the difference between a smooth cut and stopping the machine every 5 minutes to change a tool.
Precisely.
And rounding out the new materials, they boosted their deep drilling line with IC948. This is aimed at ISO P and ISO M applications.
And those ISO codes just give us the context. ISO P is steel, ISO M is stainless steel.
Right.
Deep drilling in these is really challenging. Chip evacuation is a nightmare. Heat builds up like crazy. IC948 is engineered for just sheer toughness and resilience in those core materials.
So when you look at all 3 hard steel, sticky titanium, deep drilling stability, the common thread is solving these high friction, high cost problems.
It's a very deliberate R&D focus. Yeah.
Here's where it gets really interesting. So once the material can handle the heat, the engineering focus shifts to geometry. We're moving from that material foundation to the actual shapes that deliver these huge productivity gains in turning.
We're moving from physics and chemistry to pure geometry and mechanical advantage. This is where you see the multiplicative gains, not just the small incremental ones.
And the innovation that just immediately jumps off the page is the POMG inserts. This is the ultimate economy driver. So it's a pentagonal double-sided insert. But the aha moment is that this design gives you 10 indexable cutting edges on one insert.
10, I mean, just think about that in terms of tooling cost per part. A common square insert gives you 8 edges.
A single-sided one only gives you 4.
Exactly. Moving to 10 is just pure operational efficiency. The machine runs longer, the operator stops less, you need less inventory. It's a huge deal.
Okay, but I have to push back a bit here. If you're stacking 10 edges on one small piece of carbide, how do you make sure it's stable? Are you trading rigidity for economy?
And that is the critical engineering challenge they had to solve. The material makes a point of saying they engineered a special periphery design for it.
To ensure that secure clamping.
To ensure a secure, stable dovetail clamping you're cutting at high speeds, if that insert shifts even a few micrometers, the part's ruined. They figured out how to get the 10 edges without compromising the secure lock.
And they gave customers options too. 2 versions, a 14.5-degree angle for high feed roughing, and a 55-degree for more standard work.
So it's designed to be a workhorse.
A universal workhorse, exactly.
Yeah.
Now, shifting just slightly to focus on heavy loads, they updated the quick turn tools. These use the Q6 MNMG inserts with this unique concave hexagonal geometry.
Again, it all comes back to security under stress.
Right.
When you're doing complex operations like multi-directional turning, profiling, and facing at the same time, you're putting these extreme changing loads on the insert. That concave hexagonal shape creates a self-centering, self-locking mechanism.
So it's engineered to just lock itself down.
It lets the customer push the machine to its limits without risking failure.
And finally, let's talk pure speed with quick thread. This is their multi-tooth insert line for cutting standardized threads.
And this is where the headline number is genuinely transformative.
I saw this. It can cut threading passes by up to 75%.
75%. Think about a normal threading operation. You're making dozens of shallow cuts to build that profile.
Right, pass after pass after pass.
If you can get the same quality thread in a quarter of the passes, the cycle time savings are just immediate and immense.
How do they even do that without just shattering the insert? I mean, that's not just a speed tweak, that's a whole different approach, isn't it?
It is. It's done with a multi-tooth design, so multiple teeth are engaged at once. The geometry of those teeth and the chip breaking action they have lets the tool remove material way more aggressively, and it spreads the load across the insert.
So for a high-volume threading shop, that's just more parts per hour.
It's more throughput and lower costs, plain and simple.
So the turning advancements are all about maximizing runtime and just raw speed. Do they keep that same focus on throughput when we look at milling?
They absolutely do, but the focus shifts a little. It becomes less about minimizing passes and more about minimizing cutting forces and improving chip evacuation. Those are the big hurdles in milling.
Okay, let's transition then to shaping and slotting to milling. First up is tang disc, which is for high-density slot milling.
Wow.
It uses tangentially clamped carbide inserts.
And tangentially clamped is the key phrase there.
Why is that so important?
Well, with a normal radially clamped insert, the cutting forces are trying to push the insert out of its pocket.
Okay, I see.
With tangential clamping, the main force actually pushes the insert deeper and more securely into its pocket. It dramatically increases stability, which allows for much heavier, higher density cutting.
And I see it has an internal coolant supply built in. I'm guessing that's not optional for slotting.
Oh, not at all. When you're cutting a deep slot, the tool is almost completely enclosed.
So the heat has nowhere to go.
Exactly. Heat is immense, and getting chips out is a nightmare. The internal coolant flushes that zone, manages the temperature, and makes sure those chips get out so they don't get recut.
Okay, then on the face milling side, we have the expansion of the Neodu family. They've shifted to a smaller insert that still has 8 cutting edges.
And the benefit of that smaller size and its specific geometry is lower cutting forces. If you're just milling a big flat block, cutting force isn't always the main concern. But imagine you're milling a pocket right up against a thin wall or a shoulder.
They can't have the tool pushing sideways.
You can't. You need the force directed down and in to avoid damaging that adjacent surface. Neodo excels in those space-restricted areas.
This focus on heat and forces brings us to something that seems to underpin all their high-performance tools.
Yeah.
Targeted coolant delivery.
Yes. High-pressure cooling and MQL, or minimum quantity lubrication.
And this is where the material science and the tool geometry finally meet. the shop floor reality.
It is. You need high-pressure cooling for the materials we talked about, the superalloys, titanium, advanced stainless steels. You have to blast the chips away and keep that cutting zone stable. If you don't, the tool's advanced coating just can't perform at its limit.
It ensures that investment in the tool actually pays off.
That's it, exactly.
All right, let's transition to hole making before we hit the digital side of things. ISCAR took their successful quick 3-cam design and applied it to countersinking with these new F3B heads.
Which is just smart platform leverage, right? The heads mount on existing tool bodies, so it simplifies inventory for the customer.
Right.
But the real benefits are straightness, concentricity, and a superior surface finish in the countersink. They're taking a stable drilling tech and applying it to a finishing operation.
And the detail that really stood out to me was the special chip deflector geometry. Why is actively breaking the chips so important, especially in hole making?
So imagine drilling something sticky like stainless steel. The chips don't break. They form these long, sharp, stringy ribbons.
I can picture that.
And those ribbons wrap around the tool. They increase friction. They can score the inside of the hole.
And in a worst case scenario, just jam a whole machine.
A catastrophic failure.
Yeah.
So that deflector geometry actively curls and fractures those chips into small, manageable pieces. It ensures a smooth, reliable process, even in the toughest alloys.
That one detail really crystallizes the level of engineering we're talking about, which I think leads us perfectly to the final piece of the puzzle, the digital twin. It's clear ISCAR believes every tool has two parts now, its physical form
and its digital counterpart. It's the required merging of hardware and software. You can't just pick a tool off a shelf anymore. You need to simulate its performance, predict its life, and optimize everything before you put expensive material on the machine.
It's all about planning.
Right. So the e-catalogs, the data formats, the expert software, it's all designed to make that planning easier and more accurate.
And for 2025, the updates were mainly focused on usability. New filters in the e-catalogs to speed up searches.
Which is helpful, but the more significant advance is the expansion of their Neo-ITA expert system.
Okay, what does that do?
It's a powerful system that helps you make decisions. It gives you cutting data, predicts tool life, and critically gives you cost estimates. And now it's been expanded to include T-slot milling.
So it shifts the complexity from the operator on the floor to the planner at the desk.
Precisely. Instead of relying on tribal knowledge or trial and error, a planner can use it to predict the true cost per part and find the optimal parameters. It means better planning, fewer surprises, and more accurate job costing.
So what does this all mean if we step back and look at ISCAR's whole gathering stones exercise for 2025? It feels like three big trends really stand out.
I think so. First, that dedication to highly specific material grades. They aren't trying to make a one-size-fits-all tool. They are tailoring chemistry to solve unique, high-cost problems.
Like with the hard steel and the sticky titanium, it's focused material warfare.
It really is.
Second, there's that absolute, just relentless push for insert economy and speed. I mean, the innovations are all about maximizing value and throughput, whether it's the 10 indexable cutting edges on those POMG inserts.
Or the claim that quick thread can cut passes by up to 75%.
Right, they're just slashing downtime and cranking up the feed rates.
And finally, that essential digital integration. Every physical tool is now linked to a digital twin and a robust data set.
Yeah, the expansion of Neo-ITA really shows that commitment to making sure the tool's peak performance is actually achieved on the shop floor through better digital planning.
It's all connected.
This deep dive really highlights ISCAR's core belief that even these seemingly small, highly engineered advancements at the very tip of a tool can create an enormous impact in the wider industrial world.
Exactly. The next time you see any complex manufactured good, an aerospace valve, a perfectly smooth engine component, just take a second to think about the hidden complexity that was required to shape those materials.
What does the efficiency gain from something like 10 indexable cutting edges or a 75% reduction in threading passes? What does that ultimately enable the industrial world to create faster and cheaper? That engineering resilience is what's really driving global production forward. Keep that thought with you.